Hey, good morning, everybody. It's 10:55 Eastern Time. We will start around 11:02 just to give some people time to join. In the meantime, if you take a look at the current slide for some instructions on how to ask questions during this event, if you take a look at the top right-hand corner, you'll see a little question box with a question mark in it. If you click that, you'll be able to type questions during this event. Also, if you click on anonymous, please type your name in so we know who's asking the question, and we'll begin shortly. Thank you. Hey, good morning, everybody, and welcome to the Swiss Advanced Applications Review by Brian Such. I hope you all enjoy this event. Brian, it's all yours.
Thank you, Joe. Welcome, everybody. As we try to get through our pandemic here, MCC has tried many different web events to keep your interest going. And so as we are reviewing many topics, we thought that one of the advanced applications events could be useful. And so we're bringing this to you today. As this slide just loads on the beginning of this presentation, I'd like to explain just a little bit of background. So, I'm dating myself and us, but many years ago we were asked to put together an advanced applications, and you could look at it many different ways. Deep programming, deep macro things, and really advanced applications is not just the G code of the programming of how to get there. It's more so the idea of what you want to do. And so an interesting statement that makes this a very powerful presentation for me, and hopefully for you, is we gave a presentation up in Productivity, Minnesota, our dealer in Minnesota. And it went over well, and it was basically this presentation. This has a little bit more and a little bit less, and it's been changed over the years, but it's basically the same presentation. And all went well. I visited some customers in Nebraska maybe 8 months later, and the shop owner actually said, "Hey, great to see you. Thanks so much for training our staff. When they came back from your training, we saw a 15% improvement of parts going through the shop within 2 weeks of them coming back." And we talked and we explained, "Hey, that's fantastic. That's great to hear. But I didn't do any training in Nebraska. So whoever should get the credit, I want to spread the credit. And it wasn't me." And they said, "Well, they came up to Productivity and they saw a 2-hour event that really is a lecture. It's a presentation. After they saw this event, they went back to their shop and maybe they didn't even do some of these things, maybe they did, but it gave them a new perspective, a way to look at what are we doing and what might we do." And so with that, I wanted to start there is what a powerful thing, just some sight of what others have done, and we'll continue here. So with that, we have ideas about collets, different types of interpolation methods of its programming, but methods. Definitely, we're going to review some superimposition and how it helps us. Simple supports, but a lot of people aren't thinking of supports. Polygon's a big subject, servo torque sensing. So we're going to review all these things and let's get going. So when we look at special collets, everybody's done some of this, but some people, look at it simpler, and some have done very deep things. So we have to start somewhere. So in this case, when we utilize a shaped collet, we have to remember that we might need an option. And here's what we call the chuck sleeve. And we have to have a keyed chuck sleeve. A standard Swiss has no key here because it's a round collet. It's not needed. And then your collet has to be made with a keyway in it to fit the key. And actually, we sell these, it's all on our quotes, but also many customers can modify our current sleeve, drill a hole. This is all very hard, but customers do it. And so you have many ways to produce this effect, but just to remember, you need keys to hold these. And so the next thing that if we go way back in time, 1990, we started with some of our more advanced machinery. And when you have these odd shaped collets that's keyed, how do you know what location they are to the rest of the part? And from 1990 to today, we have a simple G code that zaps the subspindle and it knows where 0 is. So it's called phasing or phase 0. And so we have easy methods with our Cincom control to do that, where others have to fight and change parameters to find their 0 location. So let's just look at one of these. Here's a part that we had to do, a long time ago. And as you can see, it looks very tool-like. This is like a 3/8 ratchet for the auto industry or the tools industry. And this design was a high carbon steel. It's got to be heat treated. And we really, high production, we needed cycle time. We could not take the standard Swiss approach of mill, index, mill, index, mill. We had to pound this through. So we knew the only way to get the cycle time down was to use a very large set of saws, and we straddle sawed. So we have two saws with spacers, and we just pound across this and index once and come across again. And so we have two sides to do this on. And so we're trying to say, where are we going to hold this? And we elected to say that this is the guide bushing side or the front side of the part, and this would be the back. But now if you were to hold and make a collet to hold this, it's odd that, yes, in one direction it will hold very rigid, but in the other direction it's going to want to tip or tilt as we really put pressure on it. So really simple. Instead of having to say real quick, just order this collet, think about it a little, and we did a counter bore in the collet also. And now when the part fits, we don't only have it held by the flat, we have that little bit of turn portion held. And we were actually able to pound these saws, and this part was something like 52 seconds. We were under a minute, and that was our goal, and we hit that goal. And this was the first good start of an advanced applications, is to look at your collets and make sure you design them to the best of the cutting principles that you're going to use. So next is another one here. We all see these kind of parts, but we get a lot of pressure, and our customers get pressure that, we got to have these parts by Friday. So a customer, or at the time a potential customer, came into our facility, not even knowing the dealer, and said, hey, we got to run these parts. If you can run these parts, you got an order, and here's the part. And as we explained, boy, this is like the black Delrin. It's very flexible, and they don't want burrs anywhere. It's got to be all good. And like, we can't just run this by Friday. I'm going to have to order the right collet. And so we got a lot of flack from the customer saying, well, the other guys are going to do it, and they're going to get the order. And I said, well, I'm going to go through the process, and I'm going to order the collet, and when I'm ready, we'll keep communicating. And so we didn't just use a round collet. We made the collet fit our part. So most of the collet manufacturers will do anything you want. This was all Southwick and Meister. And not only did it have to be wire EDM'd all the shape, but we have this little notch here because we have to still machine this while we're in the subspindle. And so if you look at this, it's very close, but it's held all the way around. It's held here. We ran a beautiful part. And then when we were all done, it was like, afterthought. You don't always think of these things, but a reminder to you, well, somehow you got to knock the thing out. And so, it probably took us, another hour or two to whittle out a knockout device. And now you can see that the knockout's relieved for the edge of the collet. And here the part comes out. Beautiful part, beautiful concept. And yes, we did get the order. So our competitor ran them not perfect parts with little burrs. We waited our week and ran a good part. So creative ideas and collets. And then for the ones that I think we've all seen, some of the specials and just special shapes. Here's a special shape collet. And to remember that, like for this, how easy it is, if we run this part in our spindle and stop, manually bring this collet over the part and execute this G code, or on today's machines, push a button in preparation, this location is known, and now we have a very easy way to pick up this part too through strong Citizen-Cincom software. And one more simple example is in the Swiss world, it seems less used is the half hard or soft collets that you can bore yourself. And these are critical for quick running parts. Now, if you're going to run production, you should have somebody make it so it's hard. But here's a 3/16 stainless part that any time we tried to machine it, it's just acting like a bell and vibrating. And now you make your collet so that it has 2 diameters, and we can hit here and here, and this picked up perfectly, ran all day, all week, all month. It was a beautiful setup. So simple things with collets. Now let's look at the next level of collet. Here's a part that we did, and actually we've seen parts like this, but I just whittled this part out for a show as one of the IMTSs, I think 2008. And it's interesting, we instantly got 2 or 3 machine orders after this. And actually last week, our support manager came and we reviewed a project. The customer has a part that looks almost exactly like this. Of course, it's different, but it's similar. And everybody wants to do eccentric turning and eccentric threading and eccentric everything. And that adds some cycle time and use of the machine. The machinery is really moving all over the place. Well, we also have these projects that the goal is low cost, simple machine. And so this specific part has 3 different center lines. So here's a center line, there's a center line for this feature, and here's a 3rd center line. And we wanted to use the simple A20. That's what's our introductory budget basic Cincom. And so how are we going to do that? If we look at it, we have a collet made. Southwick was our friend here, and they made this. And of course, we have the slot for the chuck sleeve again. And so an eccentric collet. Now, the problem is, how are you going to pick this up? Well, we can't spin this. And so this is the part of creativity. There's the part installed in the collet. Again, but now we've learned a lot, and we know when we do special stuff like this, we have to also figure out how to eject it. And for some of you that don't know, this is we call it a standard option. It's an option, but all of our machines have it and they're available. And it's a spring-loaded knockout device that's really designed for parts with holes in them so the chips don't go through. It's called a through-hole workpiece knockout device. Well, if we change the end to be an eccentric knockout, now you can see that will line up right with the eccentric, and piece of cake, easy to make, and we were able to, the ejection for this part was easy. And now here we're going to look at the application, and I'm not going to run the whole video here, but we're going to jump forward. And so if we look at the start of this, let me get to the beginning. It happens to be mild steel, but here you can see we already have it picked up and the part is running in its eccentric. So as the front's running, the back's running. Now we have plenty of time. There's a lot to take off with this eccentric. Now I'm just going to jump ahead and get to the good stuff. This would be the 2nd center line. So that the first part we're running on normal center. We're milling the 2nd center line with milling interpolation, which we'll cover in a minute here. And then we go and finish the rest of the part. And what's interesting is how are we going to pick this up? So this is on center. And if you remember, the collet is offset. So we can't spin this. Well, try to think outside the box. Try to think, just how can we get this part? We do have an x-axis on our subspindle. So if I can stop this properly. So what we're going to do, again, this is on center. We're going to pre-cut off to a number that you determine. Might be 80 thousandths, might be 60 thousandths, enough that's going to hold the part here, but it's almost ready to fall off. What we can't see on the left here is the subspindle collet. And if we stop and lock C-axis and bring it that it's in line with the X-axis, and now bring that off-center collet on center, but not spinning. We feed it over the part, and then all we do is close the collet, turn on the spindle, and we'll actually just twist the part off. I'm just going to run it now so you can see. So in this case, we pre-cut off. Just twist the part off. Now we have the part held, and now we have the ability to go and machine the second side, turning and threading and grooving, not needing eccentric turning. Very simple thing, thinking outside the box. If we look at even our fixed head versions, our Mianos, our BNJ, our BNA series, MSY, anything where the subspindle moves an X, we can do this same topic, and we do it. So let's look at one more. Here's another project we had that's a creative part. It's in the medical field. It happened to be a toe implant. We made it very large for a show and changed it around, and it's kind of like a horse toe implant. But so just as the example, and what this has is a bend to the part. So from the center line of this feature to the center line of this feature is a 6-degree bend. And again, this customer, this concept was, I don't want to have your high-end machine. I need to run a lot of these for the best value. And so we looked at the A20. Now you're starting to get the idea. Let's just throw a collet in there. But wait a minute, this is angled. So are we going to bend this? So the first thing we do is this bore is not a bore. So it's going to be like a sinker EDM, and I'm going to go drastic here, but this bore is in at the 6-degree angle. Now, how are we going to get this part in there at a 6-degree angle? Are we going to mill it? Well, now we lost all of our cycle time. So we need good idea, open mind, and be thinking. And so get creative, and we'll get this going here. Here the back is running from the 6-degree angle, and it's taking its time to turn. The front's just working away. Let's get this going here. And so, you know, thinking outside the box like we always want to do, let's watch this process. As we complete the front of the part, we're going to do that pre-cutoff. But after the pre-cutoff, we're actually going to bend the part. Now, once that part is bent, if you saw it, after the part was bent, we rotated it 90 degrees, so it's in line with the subspindle X-axis. And now we can take our collet that is already at that 6-degree bore, and we'll have to enter our subspindle in X and Z at a 6-degree angle. And we're going to close the collet, rip it off, and go machine. And so if you saw it move a little, what's interesting, it's going to pull it to the collet. So as much as you saw it move a little, it repeats very, very well. I can't say perfectly, but very, very well. We had a customer have a similar project after seeing some of this local in Illinois, and different part, but similar. And they ran to a very tight tolerance, and they were able to do it. So often it's just the idea to see it. So like some people just hadn't thought that this is possible. So picking up an angled part and having a bent part in the machine. And so that's a review of collets. Hopefully it opens your mind some of techniques. Now we're going to go into some other techniques, milling interpolation. And I believe most of you have seen or heard of this, so I'm going to do a quick. Basically, we have an X-axis and we have a C-axis, and it's difficult to program in the polar world. And so when we have a real axis X and a real axis C, and we want to do blended moves, it's all math. You know, our high school training is our friend, pi times diameter to give us the circumference and come up with numbers. Kind of difficult. And many years ago, we used to have to do this. We would have 720 lines of code for this little shape we're doing. Then it's awful little and you want cutter compensation and you have to reprogram the code. So with milling interpolation, a function that we've had standard in the machines from the 90s, we make virtual axis. We do a G code and it turns this function into pretending we're on a milling machine. And we're going to program a virtual axis up and down as if it's not on the Swiss lathe. And we're going to program the mill going around. And in reality, it does C-axis and X-axis moves. Click that again there. And we're able to get complex shapes in a easy to program method. And so, again, this is more common today, so I'm going to go quicker on this one. But basically, for those of you that are new to this, if we just take a G code and just call it as simple as we want to turn this function on, from there, we're programming in the real world of X and Y, just as if we were on a milling machine. So you just saw a square being cut. So here's an X150 and a Y150 and an X150 and a Y. Very straightforward programming. So what, 6-8 lines of code where, 20 years ago, this would have to be 720 lines of code. So, milling interpolation is our friend. It's a great way to, if you don't have a Y-axis, to get some shapes going. And so basically all you need is a C-axis and a live face tool in any way, and we can do milling interpolation. But what's more interesting is added on to milling interpolation is another plane called the cylindrical plane. And this is where a lot of our customers and users maybe know about it, but a lot of them don't know. They haven't seen this yet. And so this one is really opens eyes for some of the operators and programmers that simply have a cross hole. And we want to, when we chamfer a cross hole, there's always a very large side of the chamfer and a little short side of the chamfer, because we're plunging in X and there's a cylinder. And so we can basically evenly chamfer all the way around the part utilizing the cylindrical plane. And then often a lot of our customers have some kind of a J slot or cylindrical cam grooves. So I always say, a video and a picture does 1,000 words. So let's look at this one. In this case, just all simulation, but here's a simple cam groove. I think we've all seen them. Some of us have machined them. But when we run something like this, it could be a tight tolerance. And so if we start sharpening our end mill and putting different end mills, we don't want to reprogram. So all of this will work with tool nose radius compensation, and we just change an offset for the radius value. So very easy to program, very easy to utilize. There's a even chamfer all the way around the cross hole. And so many people would say, boy, that looked like, it's probably really hard to program. And so again, we're not here to teach you programming, but if we could take that cylinder, let me go back. If we could take this circle, the part, and put a line through it and magically unwrap it, unwind it, and make it flat, which would be pi times diameter, would give us the circumference of the circle. And if we did that and put it on a piece of paper, here's the flat paper, here's our cam slot that we just did, our cam groove. And we simply can program pretending it's a milling machine and come to, if the center of this is Y0, I'll go to the next slide here. We can simply program point to point G1, G2, G1, G2. And so let's look for a second. Here's this milling interpolation code. Here's this new cylindrical command. Now it's simple programming. I can take the code from here and program it. Y, comma C. This is a 30 thousandths chamfer. Z 375. See the 375 here? And we have a comma R to put this radius. And so point-to-point programming with cutter comp. We used a 125 end mill. Maybe it was 123. Maybe it was 126. We can just change the offset to get the slot. Then if we look at that, at the end of that video was a chamfering of a cross hole. Basically center the tool, call up the cylindrical, and basically feed the cutter to touch, do one circle of circle programming, the G2, and get out of there. So really one line of code. Again, many years ago, I would do that chamfer. It would be 720 lines of code, 360 lines of code. Here's really one line of code. So the cylindrical plane is a wonderful tool for our operators and programmers, and many don't know it exists. So please spread the word. So Joe, I don't know, I'm going at a high rate. If there's any questions pop up, please just jump in.
Yes, actually, one just jumped in. In the G16 C375, what is the C3.375 related to?
Okay. What this is just like we have to do pi times diameter so we can figure out how to do math. This is a radial representation of the diameter. So that part you saw running was 750. This is 750 bar stock. So this example would be half of that. It's the radial value, and it's describing basically where it's going to do the math to do all these shapes. And it's that simple. It's the diameter at which that it's working.
Another question is, could you do this with any material?
Definitely any material, sure. It's just programming code. That is correct.
And are these program software features like milling interpolation standard on the Cincom machines?
So milling interpolation is standard on our Fanucs and our Mitsubishis for many years. Angular interpolation, so the cylindrical plane is standard on our Mitsubishi machines almost forever, back to the L5, which is in the 1990, somewhere in there. On our Fanuc A20, there's still an option for the cylindrical plane. So most 90% and 95% of our machines, it's all standard. Couple machines, there's small option. And so I will continue. Thank you for the questions. By all means, keep putting them in, and Joe, keep popping them up. So we're going to move on to another feature that a lot of people hear about and don't really know. A lot of people want to do angled cross hole, but then we get a lot of parts that come with whole angled surfaces, whole angled features. And it's not like it's surfacing that's a ball nose end mill, but it's a feature that's at an angle. And if we don't have codes to help us, we have to program 3 and 4 axes simultaneously. And I think you and I know that you and I are not going to do this. This is CAD system, CAM system. And so because we do have tools to come in at angles, and a lot of our machines have standard the ability to do an adjusted angle holder, we now, and for many years, have a G code that makes angular interpolation. And this will, again, kind of like milling interpolation, will make a virtual set of axes. And basically, to keep it the simplest, we can pretend we're on a milling machine and we're not at an angle on this CNC lathe, on this Swiss lathe. And so, again, a video probably explains it the best. We have it to the beginning of the part, so you at least have a picture of the part here. So here we have a part that we did a long time ago. That's big stainless, it's 1 1/4 inch stainless, and it has 2 angled fittings coming off of it. And so, you know, quite complex. This specific machine happens to be an M, doesn't matter. So as we start machining the part, we started And so after we created the basic shape, we have multiple tools coming in from our turret with angled turret with angled, they're fixed angle. It's not a programmable angle. So this tool is set at an angle. And if you could start to imagine, you know, we have an x-axis, we have a y-axis that's as it's milling, and we have a z-axis. And this is all code. This is lots of numbers. And so when we utilize this function, angular interpolation, we can pretend that we don't have all of this and we're on a milling machine. And z is the tool. So the Z goes down the center line of the tool. And so if we continue to watch here for a second, look at all this path. Here we are milling these shapes, and probably the most creative one that, you know, people like to see is thread milling. But here a lot of our customers do peck drill. And so when you don't have these codes, you have a lot of angle, you have X and Z, X and Z, X and Z. And in this case, we're just doing G83. We're going to peck drill G83 just like you would on a face drill. And if I jump this ahead, here's a thread mill coming in. And, you know, of course, not only are we doing a circle, but we have to come out at a perfect pitch. And we have to hold a perfect diameter. So we need tool nose radius compensation and offset 1/10 and 2/10. And so, you know, this looks great. It looks, how hard is it to program? Well, it's pretending you're on a milling machine, and it's not hard to program. And so if we take the quick look, let me see if I can get past this. And so, you know, we call up a tool, and I highlighted, this is the G code that says we are now going to create a virtual world and do a rotated plane at 45-degree plane. We have to get to the center of our tool here, but now we pretend we're on a milling machine. The Z is the tool length. It comes into a length. We do cutter comp on. We do a quarter rotation. This would be your logic for thread milling. Everybody might have their own method, or each cutting manufacturer might suggest something. This specific one is a simple quarter radius in. Now that it's engaged, a full circle, and then a quarter radius out. Now,
Brian, we have a question here, sorry.
Okay.
G16, can it be used to chamfer inside cross holes? Looks like the tool may break due to C-axis movement.
On the inside, your tool would have to make the shape that you could. You actually could. It's depending on how you look at these angles. It's not a perfect 90 because we are rotating around and the tool's 90, but it is an even chamfer. We have other codes, and CAM system can make more perfect. On the inside is not only a sphere, it depends on what else. So if you're coming through the second hole, sometimes there's a challenge on the shape, but on many parts, yes, you can. On all parts, maybe not. Some parts are different. We do have other commands that are 3D chamfering command. It is a little option that we could look at, not discussed in this event. Okay, so I'm going to continue with the angular. And the point is that Z is the tool and easy programming. And so, again, trying to think outside the box. We have so many people say, well, I have that fancy M with all these angle tools, but I don't have that fancy M machine. So therefore, I don't really think I need angle stuff. Well, here's a part that we were given that's it's a site. It's actually a site for the military. And the feature is, there's an angled feature with an angled hole. This hole is not straight in, and 90 degrees opposed to that, perpendicular, is a slot. And so there's two angled features, which means, you know, multiple angle tools and B-axis stuff. It starts getting expensive, but we wanted to think outside the box. And if I look at our L series for many years, we have tool holders that we can mount in that we can be tools at 90 degrees or all the way around to 0 degrees, or anywhere in between. So we have adjustable tool blocks on our L series for many years, and we still do today. But we need two separate angles. And so Citizen didn't design this for us. It's not for this, but I did maybe the wrong thing, anything to be creative. This block can also hold a tool that's a face tool or a cross tool, and that's designed to be at 90 degrees. So you have 90 or face, and we can utilize that. So what we did was we rotated that at 30 degrees, and now we have the two features we need. Simple, think outside the box. It can't work for every part, but it did work for this part. Let's take a look. And so if we look at this feature, there's an angled hole, you'll see in a minute, and perpendicular to it, a slot, and a little keyway slot. And so I can skip the beginning here. We're whittling away the beginning of a part. Oop, that's too fast, too much. So we created the surface of the part. And now we have, utilizing our G173, angular interpolation, we can peck drill a hole. There's our creative use of the holder. Now we can go and when we make our adjustment, we typically wouldn't just do this. We'd put an indicator on the side and make sure we have a perfect adjustment. And now after that cross hole, now we come in, and this programming is X and Y, simple, Z. So we're on this virtual plane, very easy to program, very easy to offset. And when that's done, we always make little burrs, right? So come in and deburr, come in and deburr. So angular interpolation, not just for cross holes, many, many different things. So I'm going to move on to many subjects here. Superimposition. I would say, the Cincom control and superimposition go together. This is the backbone of Citizen-Cincom. But still, a lot of people today don't utilize all of our features, and we want to make you aware of them. And it's simply superimposition is one axis to follow or mirror another axis, but still be fully programmable and move independently. You can even have 2 or 3 axes, multiple superimposed, a pretty neat feature. We're going to show you this. This function actually holds in rapid motion, and it's easy to program. And now take it back. I left my old slides in here because they're key. We had and utilized this technology since 1990. So some of you old timers out there, some of our sales that are watching, and even new customers, this is your first time. This is an old E32 from 1989, and this is a superimposed set of cutting where we're turning and grooving simultaneously. But then a lot of people see us at the shows today and we're doing 2 threads simultaneously, like, holy cow, look at that new technology. We've been doing this since 1990, 2 threads simultaneously. So superimposition, many things we can do. It's not absolutely for everything, but many things we can do. And the next part about this presentation and keeping an open mind, people tend to lock into what they see. And they have seen superimpose for drilling and turning, or they've seen superimpose for turning and turning. So some people just can't get it in their head that, well, superimpose is not turning. Superimpose is one axis to follow another axis. It's anything, supports, milling. And so in this example, we had a customer that challenged us, if you could run this part faster than the Tornos Deco, we're going to buy machines. And this customer today has, 150 Cincoms. So we beat the Tornos time. How do we do it? Let's utilize every piece of the machine that we can and use superimposition and get multiple features simultaneously. So here's the indexing let us do it. These holes are multiple. And here's angled cross hole while we do cross hole. Great, simple little thing. But let's go to the next. This, again, this is back for some time. This happens to be an M series. We have M today, C series, and we have many that can do this, our D series today. And so here's multi-axis superimposition. As we're turning, we're spotting and drilling and pecking, indexing the turret while it's spotting and drilling on the back. Utilizing all of the axis as much as we can, 3 tools in the cut. Now, can we do this on every job? No, but we can do it on a lot of jobs. And I think a lot of people get into the mindset of, yeah, but that's hard to program. It really is not. You have to get past the thought of difficult, and it's almost as simple as adding 1 G code. And we have another example towards the end of this that we're going to show you some of that. So multi-axis superimposition, fantastic Cincom technology. So here's a part I'm going to kind of fly through that we were challenged we're a member of the PMPA, and they had asked us to do seminars on cycle time reduction. And I brought up the point and the fact of superimposition. And so there's another portion of superimposition many people don't know, and it's called superimposed spindles. And so we're going to look at that part you just saw. And if we look at what everybody does the normal way, and I didn't have it in video, so I made a little esprit thing here. But if we're going to drill a part, we typically center drill, stop everything, and tap. So this is very normal process Swiss. Then we go on and turn. This is how we live. This is Swiss. Now, we just learned superimpose, right? So as we're learning, you say, well, Brian, we definitely can probably get that whole simultaneously. And so if we were to do what most of us might start thinking just from this presentation, well, as I'm turning, I can spot and drill. But think about it for a second. If I have to tap this, I cannot be spinning. So I'm going to have to spot and drill as I'm turning. And sooner or later, I have to stop the spindle, bring the tap over, bring it in, reverse the spindle, bring it out, right? This would be normal tapping, and really the only way to tap. Well, I'm going to challenge you and say, watch what we can do. And I want to say we could do it for many years. This is not new for us. Not all of our machines have it as standard, but as long as you have a live face tool. So for example, today's machines, the Type 10s and the Type 12s, can all do this. So let's get through the beginning stuff. And here's a part with the million features we saw. I'm going to stop the sound here. And so we're going to do another view closer, but you can see it was spotted. Whoa, what's that? The tap came in. Well, I'm going to blow that up for you. Whoa, went to the beginning. Sorry. Oop, back her up a little. Here's the beginning. And so if we look at this concept, this technology, of course we can center drill, but how are we going to put that tap in there? Well, we have another feature called superimposed spindle. So one spindle can follow a spindle, but still be programmable. We are still turning. The Z-axis is still moving. We've turned on that tap. This is a rigid tap. It is not floating. And it's a combination of the superimpose code and spindle superimpose. And what do you save? You don't have to reverse the spindle. We get it simultaneous. We save 6 seconds, 7 seconds. You got to look at the whole part, but this actual whole part in steel, here's angular interpolation, happens to be a B-axis machine. So we're adding to all the things we've already been learning. But if we look at this, boy, Brian, the way you're showing that, I'm sure that we need high-level programmers and kind of rocket scientists, and we don't have programmers like that. We're going to have a hard time. Well, let's look at that part that we just saw. We basically turn on superimposition, and the turning tool starts running, and it's at 4,000 RPM. But of course, there has to be some talking. We can't have the spot go in if the turn's going to face, the two tools are going to smash into each other. So as the turn goes in and does the chamfer, and it's ready to start on its long turn, we send a talking code. So that's one little thing we had to add. From there, we turn. As we're turning, we spot, but we don't do weird stuff. We spot 100 thousandths deep, 110, I'm sorry, and a feed rate of 2 thou per rev. Now this one's feeding at, where are we here? We're feeding at 3 thou per rev. So it knows, it just does it. We call up a drill and do a peck drill cycle. It just does it. There's no rocket science. And now you're going to say, well, but that tap had to be rocket science. Well, let's look at the code for the tap. Look what Citizen has given us. We say, make the tap spin at 0 RPM. That's interesting. Okay, whatever. So we have a live tool tap that's spinning at 0. Here's the spindle superimpose. Tell the number 4 spindle, that's this one, to superimpose onto the main spindle. And now, instantly, the main spindle's going 4,000, and so this tap is going 0. So it's going negative 4,000. It's going 0 RPM. And now here's a rigid tapping command for anybody who knows how to tap, and we just program 1,000 RPM. This is no difference. This is how we would tap on any machine we've ever had since 1990. All we did was add this code, and we get that tap going in and out simultaneously. I have to say, it's easy to program. So superimpose is our friend, and I would encourage any and all to start looking for ways to utilize superimposition. I will give a second to ask Joe, how's the questions doing?
So far, so good, Brian.
Okay, thank you. So next is a whole nother category, work supports. Work supports can be done in many different ways. Here's the examples of what we have trouble on a Swiss. This was an old example, but here's a heavily turned part with another diameter, heavily turned, another diameter, and a long milling feature. Well, what's the problem on a Swiss? If we turn that long and pull back, we are totally out of the guide bushing. And 99% of our Swiss users would secondary this feature and say it can't be done, it is not possible. So we either won't quote or we'll secondary it and add cost. Well, thinking simply outside the box, or today, a lot of people do this, let's put a support. So we turn the device, pull it into the guide bushing, bring in a support we make, put the part into the support, and now we put a saw in there, and I think we sawed this at like 50 inches a minute. Nice and rigid, it's held. And so this was a two-sided machine, a two-turret machine. Simple support ideas. Let's look at another. Here's one crazy application. This was 58 to 60 RC. This was pre-heat treated material. I thought the milling would be my nightmare. Here's turning this whole way, a change in diameter, and milling. It ended up that the cutoff was the problem with this part. There's a tap, that worked. But what I thought was going to be difficult with this milling, as long as you have it well supported, the mill does its job. Again, we made a support. We had a window in the support, so the mill could go right through. And this was as rigid or more rigid than a milling machine. It was held 360 degrees, just a fantastic method. And the problem was the cutoff. And what we did was we did just like those previous parts of the Eccentric. We pre-cut off, stopped, and ripped the part off. And then our cutoff lasted. So many things that we can do. Now I'm going to go into a whole nother topic, and I have a creative presentation here for you. So Polygon's desired by many, and basically it's a timing of the spindles. And so if we look at this, I leave this again, an old video in because it shows the process the best. This happens to be M-Series. M-Series, we actually sell a holder, and there's some cost to that, but we can program multiple diameters, and we have flats, and everybody wants to do flats. what people don't understand is how aggressive this is. So if I turn the volume, sorry. I purposely wanted to give you that. So it's a very aggressive feature, but this shows the concept. It's a timing of the main spindle, a timing of the live spindle, and you get a near flat surface. It cannot be flat. Well, how flat or how not flat is it? And when can I polygon? And so many of our customers and many of our dealers would say, Brian, what holder can I use? Where do I buy it? Where do I get the cutting tools for it and the inserts? And then how much error will be on the flat? And as many years ago, I didn't have all these answers. And if I ask around, it didn't seem like anybody had all of the answers. And so if we go to our higher end machines, yes, we have turrets and we have holders, but what if I don't have a high end machine? What if I want to do it on a simple L machine? And so basically any machine that has a face live tool can polygon. You know, where do I get cutter holders? The big companies, Schwanog and Horn and others, they sell big cutting holders, but big cutting holders don't fit in Swiss machines. So I'm going to say here, you might have to design your own. How much error will be on the flat? I still cannot find calculations for this, so I'm going to show you what I did. So here's an example of a part that we had. It's a great success story. We were given this part with, it's a 70,000 square, and on this square shape, it had to blend out. So there was no holder to buy. So interesting, and I want to encourage our managers out there and all of our operators and programmers is you have to have persistence. You can't just say that didn't work. So a quick story, I'm going to waste time, but so I had two young guys during this time. Customer came in and wanted this part, and I never polygoned before. This would be my first experience. And so I had one of my young guys and I said, we should try to polygon. And they said, I heard of that, let's do it. How do we do it? I said, I'm not sure. I started digging around the drawers and I found this cutter. This was like a 10-tooth cutter. And I said, hey, go take this cutter and grind off all the teeth and just leave two teeth 180 degrees apart. And they questioned, well, why do you want to do that? I said, just do it. And so they finally do it. I'm in working on the machine. We put the cutter in. We took the G code, put the G code in. And when it first cut, it sounded very rough and the shape was really bad. And so now you got the naysayers and the glass half full, glass half empty. They said, my young guy said, see, it won't work. I said, well, hold on. I see that it will work, but we have not a good cutter. So we took the cutter out and we put more clearance on these teeth. This is a saw, like we had to change it a little. We put the cutter back in and it sounded beautiful, but the shape wasn't great. Well, this was a hand ground cutter, So my young guys are like, see, it won't work. And I'm like, no, it will work. We just need a good cutter. So I went through and started designing a cutter. I found inserts from a turning tool. Here's the part that we want to run. And so if we look at it, we started to design up a cutter, and the first cutter, it didn't work. And then the guys again, hey, it'll never work. No, it will work. It's just I don't know how to do it yet. I designed the cutter a little more, and what we found was this part ran beautifully, and we're going to show you in a second. But we used that same cutter to do a 1/2-inch hex instead of a 70 thousandths. And so the 1/2-inch hex really looked bad. And so I'm trying to say, how can we determine, is polygon good for us? And so I have an Excel file here that we can give anybody if you request it. Your dealer should have it. And if I go to our part, the part that I did was 4 flats with 2 cutters. The flats were 70 thousandths, if you saw, and you don't know, but our cutter was 875. And if I do this and calculate from this simple thing, this is the amount of error on the flat. And look, it's 0.00002. It's virtually flat. And that's why our part looks so good. Now, if I do the same calculation with 6 flats and 1/2 inch, this is the next test part that we ran. You can see we had almost a 5/1000 dish on the part, and it didn't look good. And so instantly, you know, my guys are saying, see, you know, it won't work. And I'm like, no, we have to figure this out. So if I do the same thing, well, what if I use 3 cutters instead of 2? Let's redesign. Well, 2 thou. Well, what if I make a bigger cutter? What if I want 1.25" cutter? The point is we have to understand the technology. And so I made a little program that by 1 degree increments put the tool where the part is in the flat, and it calculates what's different. I could not find any formulas on the internet. So with this little tool and understanding the tooling we have available to us, Polygon starts to get creative. We can determine, might it be good for us? The G code for Polygon has been standard for many years. Most people don't even know they have it. So the Polygon G code is standard. You just have to get a tool in there. And so the conclusion on this whole idea is polygon milling, if it's used widely, can offer great advantages in cycle time. Some experimentation may have to be done. And basically, you got to find some way to figure out how flat will it be. Well, we have a little bit of a Excel chart to help you. And maybe you got to make your own cutter. Today, they sell 30 millimeter cutters. There's some things you can buy, but make sure you look at it many ways, and don't say if it's not available, I can't do it. Well, try to figure it out. And with that, let's take a look at Polygon. This part was a big push. We ran it. The competition ran it in 1 minute without Polygon. We ran the part in 31 seconds with Polygon. We got an 8 machine order and 8 and 10 more machines for different parts. It ends up, this was picky. This was the US government. The finish of the Polygon, they didn't like. They ended up milling it in a different way. Doesn't matter. By the end, we got 15, 18 machines in there. So good process. I want to back that up once more just so you can see it. It's a great homemade cutter. Turn on a G code. We did 2 passes, like a rough and finish. Polygon can be phased. So this part flat is in timing with milling that's from the front side. So you can see the flat is in line. Not all machines, not all axes can do that, but the L series can. And so great things for Polygon. And Polygon is not only on Swiss, of course. So here's a quick example of Miano GTY, Polygon cutter from Heimatech, insert technology from Schwanog. And so when you get on the larger machines, you can just buy everything. And in this case, Miano product doing a 1-inch hex in stainless steel. Polygon machining. So continue on, many things to show the awareness and what can we do? Self-creativity. Here's a part that we had that's 18 inches long that has, whoops, I just lost my mouse. It's 18 inches long, but it has flats on both sides of the part. Customer gave us a very strict cycle time requirement. He wanted under a minute, under 45 seconds, I'm sorry. Everything we did on a more fancy machine that has milling on both sides was always a minute. And at the time, we didn't have Y-axis on our gang machines. Today, we can put tooling in and do this on an L series. But if we keep the simpler L series and think outside the box, here's what we did. It took us a couple weeks to figure this out. The distributor keeps telling us, hey, can you find a faster way to machine this? And it ends up being thinking. And so it has nothing to do, Citizen didn't give us live tooling in the back. So, but we do have multiple live tools here. if you can throw away your preconceived concepts and forget what everybody else told you, I can set this tool and this tool at the same height. So when I program this up and down, this is going to go with it. Well, I have a Z-axis and an X-axis on the subspindle. If I bring the subspindle over and in, anything I'm milling times 2. So I have a machine that's not made for milling on both spindles, that we're milling on both spindles. And we were able to get the cycle time cut in half. Here's an 18-inch long part with mills on both sides, drills, cross holes, able to run in 31 seconds with 2 rechucks. It's going to zoom in a second, so we'll run it a little bit bigger. Long workpiece device to get shafts out of the machine. Got the Mission Impossible theme going. So now if we blow up on it a little bit, as the back turns in grooves, the front turns in grooves, and here we simply have a mill, and we're really programming this one. This one's just sitting here, and we bring our subspindle up to it. So now we have 2 mills running simultaneously, and very low cost as far as a machine tool. And all it takes is keeping an open mind. It has nothing to do with what's the G code. 31 seconds. And as the next creativity, a lot of us do things with different drillings and tough materials and deeper and tougher, and we want to go faster. And so we start using gun drills and things. And sometimes it's a short run, and we have not implemented electronic drill breakage, and we want to get short-term or simple drill breakage. Well, we have G codes in our machines that are servo sensing commands. Now, it's not made for this purpose. Keep an open mind. I'm using a G code that's made for a different function that I want to use for me. And so what we're going to do is we're going to put a pin in a drill position and push it into a hole that was already drilled. And that pin's either going to hit material because the drill's broke, which is going to make our axis have more load, or the pin is not going to hit anything because the drill's good. And so one G code that says feed under torque checking, go to this position, and if you reach 30% of load, stop moving. I'm not here to teach you programming, but a macro variable to record the position we're at. And we can say, if we made it to the position, continue. If we didn't, we can actually make an alarm. The starter drill is broken. And so very simple things with our self-creativity, servo torque sensing, and let's take a look. Today, the tooling manufacturers have technology. So this is 316 stainless, it's brass for the video. And that pre-drill, they wanted us to go 4 thou per rev at, a billion surface footage, however you want to do it. And, we're going into a show. You guys are going into production. If this drill breaks, the gun drill breaks, the next drill breaks, drills on the backside break because the hole's supposed to be there. And it's just a nightmare. So we got to know if this drill is broken. So I'm going to run it one more time here. And so after that drill penetrates and it does what it's supposed to do, we go and check. Did the drill break? We just pushed a pin in there. Nice and simple. Use the same technology for a cross hole. Doesn't mean it's doesn't mean it's the only way. So if we drill some cross holes here, back up just a little, put a pin in. Did we hit anything? No. Move on, let the tap come in. Otherwise, we got broken tap, right? Another feature. Sometimes we do heavy milling. Here's a big mill. We're going to bring in a smaller mill for the next feature. Well, it's going to instantly break if this mill just buries into material. So after this mill's done, before the little mill, we're going to come out, bring that same pin, and check. Is it milled? Yes, it is. Now our little 1/8 inch mill can come in. Self-creativity. Go to the extreme. Please don't take this, but not that we can measure with a probe and be 1/10, but here we used it for part gauging. We found easily under a thou we can measure, and with creative programming not taught here, we can actually update the offsets, and we can make a programmable diameter checker with offset capability. Self-creativity, servo torque sensing. So now let's look at another. Everything goes into a story, and I think you'll really, this is a, I don't know, a cute story. I kind of like it. So we had a customer that basically had a very large bundle of 875 aluminum hex bar, and the owner, you know, whatever happened, we installed the machine, the dealer did, machine's running fine, and like a month later, all of a sudden, you know, of course, it's blamed that the machine is bad. And so they had a 4-inch long part, had a through hole, and there was a slot about 3 inches long that had to be perpendicular to the hex flats. And so you very easily can see when this slot is not lined up with the hex, and they needed it lined up. And it wasn't 1 degree or anything. They only needed like 5 degrees. But all of a sudden, the parts were running good. A new bundle of stock came, and all of a sudden it's, you know, 8 to 10 degrees out of the slot and hex lining up. And so instantly they all say, you know, the C-axis is broken, the C-axis is not repeating. But basically everybody blames the machine first. And so I was called in and we went to look, and basically if I took the remnant from the bar feeder and put it on a surface plate, you could rock it almost 1/4 inch. You know, this is how twisted and bent this bar stock is. Well, not to say anything about anybody, this happened to be a woman shop owner, and as we explained and showed this, we said, you know, you need new stock. There's nothing we can do. I think they were in tight times, and I could see tears in her eyes, and it was 6 o'clock at night or whatever. I said, hey, I'm sorry, there's nothing more we can do. It's not our machine problem, and she understood. I left, I was driving home. I probably got 1-2 exits down the freeway, and like a light bulb came on. I've been using that servo torque sensing for drill checking. What if I use that technology here? I called them back, said, can I come back? And they instantly, yeah, come on, we're still here. I asked the operator, go get me a ball nose end mill, a 187 ball nose end mill. What kind? I don't care, the round kind, you know, ball nose end mill. And we didn't mill anything. We had put it in a live tool. We came in and did servo sensing at this crooked bar stock. Then I went to the other side, did servo sensing. I could do math from where it sensed. I could move the machine 3 or 5 or 8 degrees, whatever it needed. And so we could adjust for every part. Basically, here's that G code. Remember the position. Move over in Y, our axis along the milling axis. Do the G code. Remember the answer. Do a math. The arctan, this high school trig here. So we do a little bit of math, and we determine by math that it's 7 degrees out. We move the C-axis 7 degrees and run this part. Basically, a good idea, thinking outside the box. They were able to run this bad bundle of bar stock, added about 2 to 3 seconds, not a big deal, and the customer was very happy. So
we got 2 questions here.
Okay.
The sensing, can it be done on any Citizen lathe and any axis?
Okay, those are deep questions. So any Citizen lathe, no. Most of all of our Mitsubishi, some of our Fanics, but the Fanic technology is a little bit different. So to make the answer simple, I'm going to say all of our Mitsubishis. and it can only be done on non-superimposed axis. So if you're trying to do multiple things and you have superimposition, servo sensing cannot be done while superimposition's on. And so a small negative is we have our own calve bar feeders, and the bar feeder is an axis and it follows Z1. So on some of our machines, there's some restrictions with utilizing the calve, but on the process that you just saw, we use Z2 instead, and so we're still able to do it. And so it's on most of our machines. It's on any machines that are not a virtual axis and not under superimposition. Big long answer, but that's the official answer.
And one more, can polygon be done on any spindle, on the sub-spindle, sorry?
Oh, definitely. And so the video you saw was the sub-spindle. So it could be main spindle or sub-spindle, yes. As long as you have a live tool pointing towards that spindle, we can do that, yes.
Thank you.
So keeping on with creativity, we get some examples that a guy came to us. We have this little ring, but we need to run it super process, super short cycle time. And most of us would never put this on a Swiss. So here's a tube diameter bore, no burrs, on about a 875 diameter part. Straightforward, but we want cycle time. We got this down to 12 seconds. So how did we do that? We utilized that through hole workpiece we already talked about. And I had the creative idea of, I'm not going to run a part and eject it. On a lot of our machines, the ejection is 7 seconds, 8 seconds. So if I can get rid of the ejection, I can save cycle time. So what we did was we ran and held 8 parts. And as we drilled for 8 parts, we ejected all 8 parts simultaneously. Let's take a look. Thinking outside the box. So the biggest thing is we do what's called multiple parts for chucking. So we're going to drill enough for 8 parts here. We just ejected 8 parts. The process is now starting and empty. As we run a part, we're going to pass it to the sub-spindle. We're going to come over and work on it. We got a bore to do. Not going to eject it. We're going to run the second part. Bore it, not eject it. The third part. I'm going to zoom this in so you can see we use the through hole. And basically the key is I'm not ejecting. I'm putting 8 parts in here simultaneously. And this will be a closer view. So drill enough for 8. If we had high pressure on, this would be 1 peck. There would not be pecks, but we had to turn it off for the video. And it's not brass. This is a steel that we're running, brass for video. But there's 1 part. Continue running. It's already drilled. Turn a little, bore a little, cut off. We push the first part in, grab the second part. Push the third part, push the fourth part. And simple, get creative. We were able to get this sucker to 12 seconds. It's not so often you get 12 seconds on a Swiss, but on an 1.25 inch Swiss, 12-second cycle time. Pretty interesting process. These were less than a thou tolerance. It wasn't like it was wide open. Had to have no burrs. So we had to bore every feature, chamfer every feature. So pretty cool self-creativity idea. You know, other reasons to do this, you know, some of the things we have long-term servicing things on Swiss machines, and one of the things that ends up going, if it's 6 months, a year, is the chuck fingers. And if you had 12-second cycle time, you could maybe only get 3 months out of your chuck fingers. Well, we're running 8 parts every time we utilize the chuck finger. So we're getting 8 times the life. On a Swiss, when you use the common area of the ball screw, you're always working near the guide bushing. So if you had 1 million parts to run, you're really wearing out the first inch of the ball screw. So when you use multiple parts per chucking like this, you use more of the ball screw. Some of our customers do set up a part and the machine never sees another part. Other customers change all the time. So we can do all, both, and just a good idea. And lastly is most bar feeders need some kind of a dwell to make sure that the signal came to switch from pushing versus synchronize. And so in this case, if we run 8 parts and 1 chucking, we only need 1 little dwell for 8 cycles. So it's saved, could be 0.8, it could be almost 8 seconds, 7 second savings in 8 parts. And it's easy to program. And so I am getting closer to the end. So for those of you that are wondering where we're going here, and I am going at a high rate, so I'll ask one more time, how's the questions?
So far, so good.
Okay, thank you. And so now I want to put into some technologies of learning and thinking outside the box, listening to our partners. You know, the tooling guys have lots of technology. The CAM system guys have lots of technology, and none of us can know it all. There's so much technology out there. Well, I did a project with Esprit guys and with Mitsubishi materials guys and other manufacturers and other machine technologies and mills have done a lot with what people know as trichordal milling. And this is a very special milling process that utilizes many small moves that cuts in a freer way, and we can use the whole length of an end mill, and it's cycle time related, it's machine use related, it's load on spindle and bearings and gears. So really neat technology. So I started the process and I started working with Esprit, and then I got Mitsubishi involved. And so we have a part here. This is a customer's part. It happened to be brass. And so I got permission and I changed the part. And it's similar, but it's different. And I made it all out of stainless. And we ran this at some shows, but it's 1 1/8 inch material, stainless, milled all the way down to 1 millimeter. So tons of milling, you'll see in a minute. Many cross holes, cross tapped, but the milling. Let's take a peek. So using technology, I encourage any and all of you operators to learn more of cutting and learn more of programming. And so I'll get past our machine tool. There's a part running. I think I'm going to sound back on later. But, you know, of course, we always want to try to use all of our features, right? You can see a pin we're going to use later for the torque sensing. Well, this is stainless. It's not brass, running dry. And here we're going to get our superimpose going. So a little bit of bore. Here we go with while we're rough turning, we're finished turning, get superimpose going. But now watch these end mills. I'm going to try to pause it in here. Well, when these mills start, you can't just bury an end mill. I didn't want to use more tools, and so we're helical entry, maybe a little bit slow. But this is 6.5 millimeter, but call it a 1/4 inch end mill, and there's another 1/4 inch end mill here. And in a minute, you're going to see them that they're going to be going 68 inches a minute. Currently, it's slower 20 inches a minute helical entry, going 550,000 feet, 1.5 times the end. It's 68 inches a minute.
Hey, Brian, I think you're cutting out there over the video.
Oh, okay. I'll stop it for a second. So as these mills entered, they went in at about 20 inches a minute in a helical entry. But once they got full in, they're 550,000 deep, and we're going 68 inches a minute, full depth. And with the tooling path of a CAM system, in this case, Esprit, called profit milling, and a I wouldn't say super special end mill, but a good end mill with helical design flutes that reduce vibration and increase rigidity. Utilizing these two techniques together, if you looked at the cutting load of these spindles, they're only at about 40%. Very light cutting load, but yet you see this process. So I'm going to say learning technology, learning end mills, learning your CAM softwares. It doesn't have to be a spree. There's others. There's many things that we can do to get better cutting, better cycle time, better tool life. So very interesting things. So today we talked about many things. It's in a high rate as not really a teaching, but just a vision on what some things we've done. And you can see that superimposition has lots of interesting abilities. Simple supports, utilizing different kinds of collets, looking at some of the features that Citizen has, Citizen-Cincom, that are simple programming. Got very creative with Polygon and gave you some ideas on how you can utilize Polygon. Servo sensing opens up a whole nother world. We checked the guy's bar stock instead of getting rid of his whole bundle. So basically, thinking of having an open mind. So as we look at the future and you look at your parts, you can call and we can help you with a G code. But it's hard to call and help with an idea. You need to have the ideas and we can help you execute them. So my goal today was the simple presentation to open your eyes, and I'd like to end with the beginning. Basically, I did this presentation, something very similar to it, and two guys from Nebraska traveled to Minnesota, sat for 2 hours and saw this and went home. 2 weeks later, the shop owner noticed a drastic improvement of parts through the shop and said, what's going on? Well, we learned some things and we're trying some things, and a 15% improvement of parts going through the door. So I'd like to challenge you and challenge your guys to open your eyes and look for processes and things, if it's advanced applications, or maybe it's applications that you don't know yet. And so I'd like to take this time to just maybe I'll finish my presentation and ask if there's any questions.
So far, there's no questions.
We can give it another a minute here. Sometimes there's that 20-second delay.
Yep.
So as we're going, I'll speak a little more. We have, for milling interpolation exactly, we have a seminar coming up in 2 weeks. The date is not out yet. So if you want more info on that, we'll have a seminar directly for that, and it's programming use. Next week we have A20 programming. This would be for your operators and programmers, a beginner level of an entire part process. It's a 3-day event for our A20 series. But if you have other machines, you could benefit from it also, because it's very similar. And we're going to continue to add more web events, some sales events, and some technical events like this. If you have some suggestions or some ideas of an event that you'd like to see as a dealer or as a customer, please let us know. Let your dealer know, or when you were invited to this from the person you were invited, please email them back and give them some input on our events now, this event, or maybe future events that you have ideas with. So Joe, I'll ask one more time. Any questions?
The only questions we have about getting a copy of this, just contact your local distributor. These will be saved and uploaded, and we can send you a Dropbox link to this. But perfect. Other than that,
so I'd like to take this opportunity to thank you all for attending. I know our time is all planned and special. We all have to utilize it, and take a minute to say a moment to think about America at this time, and let's all try to do things in ways to help each other And in doing that, we hopefully can help you in manufacturing also. And we wish you a good weekend and thank you for attending.
Yep. Thank you, Brian. Thank you, everybody.